There is a possibility that somewhere in the night sky, among the galaxies we treat as separate places, we are looking at the same region of space more than once. Not a copy, not another galaxy that happens to resemble it. The same physical structure seen along different paths taken by its light. The idea does not require mirrors, hidden dimensions, or any new force. It requires only that space connect back to itself. A spacecraft traveling far enough in one direction might never reach a wall or boundary. It could continue through ordinary space and eventually return from the opposite direction. The crew would not notice a seam. Locally, every measurement could remain normal. The stars would pass as expected. General relativity would continue to describe gravity around planets, galaxies, and clusters. The difference would exist only on the largest possible scale. Space would be finite, but it would have no edge. This is the question of cosmic topology, and it begins with a distinction that is easy to miss. Geometry describes how space bends nearby. Topology describes how the entire space is connected. Einstein's equations local curvature, but they do not uniquely determine the universe's global topology. A cosmos can appear flat in every region we measure and wrap around itself in a more complicated global structure. Argsiv. The simplest comparison is not the surface of a sphere. A sphere is finite and has no boundary, but its surface is curved. A topologically compact universe could instead be locally flat. Picture a rectangular room in which walking through the right wall returns you through the left, while passing through the ceiling brings you back through the floor. There are no physical walls in the real model. Opposite locations are simply the same location. Extend that logic through 3 dimensions, and a finite volume of flat space can behave as though it continues indefinitely. From inside such a universe, distance would become deceptive. A galaxy might send light toward us by more than one route. One path could be relatively direct. Another could cross the connected boundary of space, travel around the cosmos, and arrive from a different direction. Because the paths would not necessarily have equal lengths, the 2 images would show the galaxy at different stages of its history. One might reveal a mature system. Another might show the same matter billions of years earlier, before its present structure existed. We would not recognize the duplication by appearance alone. That possibility changes the meaning of the observable universe. The universe is about 13.8 billion years old, but the limit of what we can see is not a physical boundary. It is a horizons created by cosmic history, light travel, and expansion. We see distant objects as they were, not as they are now. The oldest electromagnetic signal available to us is the cosmic microwave background, released when the universe was roughly 380,000 years old. Oko Kwan Vu Tu Cho O. Beyond that surface, ordinary light cannot carry us further into the past. But the observable universe and the entire universe are not the same thing. The region visible to us may be a small part of an infinite cosmos. It may be a small part of a much larger finite cosmos, or, under some topologies, it may already contain repeated views of a total space whose true volume is smaller than the volume we think we are observing. That last possibility creates an uncomfortable problem. Astronomers count galaxies, map structures, and infer the scale of reality from light arriving across the sky. Yet if space wraps around, some of those directions may not lead to independent regions. The sky could exaggerate the amount of universe that exists. The most distant light offers a way to test this. The cosmic microwave background surrounds us as a nearly spherical shell. Tiny temperature and polarization variations across that shell record conditions in the early universe. If the shell intersects itself because space is compact, then the same ancient region could appear in 2 different directions. The overlap should produce pairs of circles carrying matching patterns. These are known as circles in the sky. They would not be painted circles visible through a telescope. They would appear statistically as corresponding sequences of hot and cold fluctuations embedded in the microwave background. Finding a convincing pair with the correct relationship would be evidence that light had reached us along different routes through a multiply connected cosmos. The background radiation is especially useful because it comes mainly from a thin ancient shell and has been mapped across almost the entire sky. The search has been made. Data from the Wilkinson Microwave Anisotropy Probe and the Planck satellite have not revealed a confirmed set of magic circles above the expected noise and foreground contamination. Planck's analyses found no evidence for the compact flat models they tested at scales smaller than the diameter of the last scattering surface. For a simple cubic 3 torus model, the constraint placed its characteristic size close to or beyond the largest scale directly accessible through this method. At first, that sounds like the question has been settled. The universe appears nearly flat. The repeated circles are absent. The simplest conclusion would be that space continues without returning. But flatness does not prove infinity. And a failed search for one signature does not eliminate every possible topology. Some connected spaces can hide their shortest loops away from our location. Some would produce correlations more subtle than obvious back-to-back circles. Research examining the full family of orientable flat topologies has shown that the allowed possibilities are broader than the simplest searches imply. In more complicated cases, the shortest closed route through space may be substantially smaller than the observable diameter, while still avoiding a detectable matched circle pattern from Earth. RSIV that leaves us in a peculiar position. We can measure the universe with extraordinary precision. We can reconstruct its composition, estimate its age, and trace fluctuations that existed before the first stars. The cosmological model fits the microwave background remarkably well. Yet none of that tells us with certainty whether space is infinite. The answer may lie beyond the horizon where no observation can reach, or it may already be hidden inside the sky we have mapped, disguised as distant regions we have counted twice. The universe may look enormous because we are seeing farther, or because the same finite reality has found more than one way to send us its light. The difficulty is that the universe does not advertise its topology locally. A person standing on Earth cannot detect the planet's global shape by measuring a few yards of ground. The surface appears flat because the curvature is spread across a scale much larger than the observer. Cosmic topology creates a more severe version of that problem. Even perfect measurements within a limited region may reveal nothing about how space closes beyond that region. This is why curvature and topology must remain separate. Curvature tells us how parallel lines behave, how triangles add up, and how distances respond to gravity. Topology asks a different question. If you continue along the straightest possible path, where can that path eventually take you? In ordinary Euclidean space, it never returns. In a compact space, it may. The distinction became physically important when general relativity replaced the idea of space as a passive stage. Matter and energy influence geometry. Geometry influences motion. The universe could now be treated as a dynamical object with a measurable shape, but Einstein's field equations do not select only one global arrangement. The same local geometry can be compatible with several topologies. Two universes may obey the same gravitational laws, contain the same average density, and display nearly identical expansion histories, while differing in one basic property. One is infinite. The other repeats after a finite distance. No local experiment would necessarily separate them. Consider a perfectly repeating city built on a flat landscape. Every block has the same dimensions. Every street continues in a straight line. A resident walking east never encounters a barrier, but after crossing enough blocks, returns to the original intersection from the west. The resident could describe the city using an endless grid. That description would work for navigation. It would also count the same buildings again and again. The more economical description would use one fundamental region. Everything outside it would be another representation of the same physical space. A compact universe can be described in the same way. Mathematicians may draw repeated copies because they are easier to visualize. But the copies are not additional territory. They are bookkeeping. The physical universe consists of one region whose boundaries are connected according to a rule. The simplest flat example is a three-dimensional torus. It is not shaped like a hollow donut sitting inside a larger space. That familiar picture applies to a two-dimensional surface embedded in 3 dimensions. A 3 torus does not need to bend into some external arena. Its defining feature is identification. Move beyond one side of the fundamental region, and you re-enter through the opposite side. There is no outside required. That point matters because the human mind tends to imagine a finite object as something contained within a larger volume. A finite planet sits in space. A finite room sits inside a building. A finite galaxy occupies part of the universe. A finite universe would not have to sit inside anything. Its volume could be limited while space itself remained all that physically exists. Asking what lies beyond it would be like asking what lies north of the North Pole. Except even that analogy is incomplete. The North Pole is a location on a curved surface. A compact cosmos may have no privileged point, no center, and no boundary where the rules change. Every observer could regard themselves as central to the observable region, while none would occupy the center of the whole. This makes cosmic topology difficult to turn into an intuitive picture. A map usually shows places arranged inside a larger frame, but if the universe is compact, the map's outer frame is misleading. Opposite edges may be the same edge. Corners that appear widely separated on paper may refer to one physical location. Distance then depends on the path. Between 2 points, there may be several routes through space. One may cross the fundamental region directly. Another may leave through one identified boundary and return through another. A third may loop more than once before arriving. Light can take any permitted route. If the universe is sufficiently small, a single astronomical event could reach us multiple times. The images would arrive from different directions and at different dates because each path would have a different length. A supernova might be recorded once, then appear again, or billions of years later along a longer route, not as a repetition in time, but as delayed light, the original. In principle, an observer could see earlier versions of their own region. The phrase sounds much more dramatic than the physics allows. We could not turn a telescope toward a distant copy of Earth and watch ourselves in real time. Any light that had circled the universe would show the planet as it existed when that light began its journey. If the route were billions of light years long, the image would predate humanity. It might predate complex life. It might show a cloud of debris before the sun had fully formed. Still, the implication is difficult to dismiss. A compact universe would contain closed routes along which information can travel, not backward through time, but back through space. The universe would become capable of presenting its own past from unexpected directions. Finding such an image would be nearly impossible by appearance alone. Galaxies change, their stars age. Their gas is consumed or expelled. They merge with neighboring systems. A duplicated galaxy seen at 2 different epochs may not resemble itself enough to be recognized. Even large structures are not simple markers. Galaxy clusters move and evolve. Matter collapses. Light is distorted by gravitational lensing. Dust obscures some wavelengths. Cosmic expansion changes the apparent properties of the same object, depending on how long its light has traveled. The sky would not display clean copies. It would display transformations. Researchers have therefore looked for statistical repetition rather than visual sameness. Patterns in the distribution of galaxies, quasars, and clusters could reveal characteristic distances that recur more often than chance allows. Pairs of objects with related properties might occupy directions predicted by a specific topology. The microwave background could contain correlations imposed by the finite dimensions of space. But every search faces the same limit. The topology must leave a pattern inside the observable region. If the shortest route around the universe is larger than the distance light has had time to cross, then no signal could have completed the loop. Space might still be finite, but its connected structure would remain invisible to us. Imagine being placed inside a circular railway so large that no train has yet completed one circuit. Every stretch of track available for inspection appears straight. Every train continues away without returning. From those observations, an infinite line would be a reasonable model. It would also be wrong. Our cosmological measurements may be trapped in that condition. The universe could close on a scale just beyond the reach of the oldest light. The evidence available to us would then imitate infinity with extraordinary precision. That is the central weakness in every claim about the universe's total size. We do not measure the whole, we measure a region by time, and time may not have given the universe enough opportunity to reveal whether any direction eventually leads back to where it began. If space repeats, the evidence may not appear as duplicated galaxies or perfect circles. It may appear as something less visible, a restriction on what the universe is allowed to contain. A musical string cannot vibrate at every possible wavelength. Only patterns that fit the length of the string can persist. Shorter waves may fit many times. A wave longer than the string cannot form wave because there is not enough room for it. A compact universe would impose a related condition on the primordial fluctuations from which galaxies eventually grew. In an infinite space, those fluctuations can exist across an unrestricted range of wavelengths. In a finite space, only modes compatible with the global connections are permitted. The topology does not merely redirect light after galaxies form. It can influence the statistical pattern that existed before stars, before planets, and before matter had assembled into anything recognizable. That pattern remains faintly visible in the cosmic microwave background. Under the standard cosmological model, the microwave sky is treated as statistically isotropic. No direction should be fundamentally preferred. The exact arrangement of hot and cold regions is random, but its statistical properties should look the same regardless of how the sky is rotated. A non-trivial topology can break that symmetry. The microwave background might still appear nearly uniform, yet correlations between distant directions could carry a hidden order. Temperature fluctuations that would normally be independent may become linked because they are different views of related regions. In mathematical descriptions, information that should remain confined to the diagonal matrix begins to appear away from it. The sky stops behaving like a collection of independent directions. This offers a search method more sensitive than looking for obvious repetitions. Even when no matched circles pass through our location, topology may alter how large-scale modes align, how power is distributed across angular scales, and how temperature and polarization patterns correlate. Recent topology research has emphasized that these off-diagonal correlations may retain detectable information after the simplest circle signatures have disappeared. Archive. There is a reason this possibility continues to attract attention. The largest patterns in the microwave background have never fit expectations as comfortably as the smaller ones. Some show less power than the simplest model predicts. Others display alignments or hemispherical differences that appear unusual. These features are often called large angle anomalies. They are real properties of the observed maps. Their meaning is not settled. Planck's final analyses found that the standard flat cosmological model still provides an excellent overall description of the data. The anomalies were not strong enough to require a new model, and several are difficult to evaluate because the largest scales contain very few independent samples. We have only one observable universe, and therefore only one realization of its largest patterns. There is no second sky against which to compare it. This limitation is known as cosmic variance, but the phrase can make the problem sound technical rather than permanent. At small scales, the sky contains enormous numbers of independent regions. Statistical claims become powerful because many samples are available. At the largest scales, the entire observable universe may provide only a handful. An apparent pattern might reflect new physics. It might reflect topology, or it might be an ordinary fluctuation that looks significant because no larger survey is possible. The evidence is trapped inside the object being measured. Topology has been proposed as one way to reduce or reorganize the largest modes. A finite domain could prevent wavelengths larger than the space from existing, potentially suppressing broad correlations across the sky. Certain topologies could also generate preferred relationships between directions without requiring any local law of physics to change. That makes the idea attractive. It does not make it confirmed. Different topologies produce different signatures. Their predictions depend on the size and shape of the fundamental domain, our location within it, and the orientation of its identifications. A model can sometimes be adjusted to resemble one anomaly while failing to explain another. Foreground removal, instrument systematics, and assumptions about the primordial fluctuation spectrum add further uncertainty. The absence of matched circles remains one of the strongest constraints. Searches using WMAP and Planck data found no convincing pairs above the noise. For loops passing through our location, this means the shortest route around space must be almost as large as, or larger than diameter of the observable last scattering surface. But that statement applies to routes through us. In most orientable flat topologies, the shortest closed path can exist somewhere else. Depending on the geometry, it may be shorter than the observable diameter by factors of several, while still avoiding Earth and producing no obvious circles in our sky. A universe can therefore contain a relatively small topological dimension without placing us where its simplest signature would be visible. Octave. The failure to find repetition does not necessarily mean there is none. It may mean we occupy the wrong location. There is another reason topology could remain hidden, and it comes from the theory often used to explain why the universe appears so smooth and flat. Inflation proposes that the early universe underwent an extremely rapid expansion. A tiny region was stretched to enormous size, diluting curvature and allowing areas now widely separated to inherit similar initial conditions. This is sometimes treated as an argument for an effectively infinite cosmos. But inflation does not determine topology. It can enlarge a compact space just as it can enlarge part of an unbounded one. If the universe began with connected directions, expansion could stretch the shortest route around it until that route became larger than everything we can observe. The topology would survive. Its evidence would not. This creates a nearly perfect observational disguise. Inflation could make a finite universe look flat, smooth, homogeneous, and much larger than the cosmic horizon. Every measurement available to us would then agree with an infinite model, not because infinity had been detected, but because the identifying boundaries had been carried beyond causal reach. The standard model would continue to work. Galaxies would form normally. Expansion would proceed normally. The microwave background would match the expected spectrum across almost every measured scale. No spacecraft would encounter an edge. No telescope would see an obvious duplicate. The global structure could remain different while all accessible physics stayed the same. This is the deeper problem with asking how large the universe is. The question appears to demand a number, yet observations may provide only a lower bound. Each improved survey can tell us that a repeating scale is not present within a larger region. None can guarantee that the scale does not exist just beyond it. We may continue extending that lower bound for centuries. The universe may continue refusing to reveal whether the bound ever ends. And if every closed route through space lies beyond the distance light has traveled since the beginning, then a finite cosmos and an infinite one are not merely difficult to distinguish. From our position, they may produce the same sky. The simplest compact universe returns light through opposite faces without changing its orientation. But there is no reason the real topology, if one exists, would have to be that simple. Space can reconnect with a twist. A photon crossing one boundary might re-enter from another direction, rotated, reflected, or displaced. A structure viewed along one route could appear turned relative to its second image. In some topologies, moving through the universe would reverse the apparent orientation of an object before bringing it back. In others, the shortest loops would depend strongly on direction. This expands the number of possible cosmic architectures far beyond a repeating box. Flat space alone admits several distinct compact topologies. Curved spaces allow many more. A positively curved universe could close on itself in a way related to a three-dimensional sphere, yet still contain additional identifications that reduce its total volume. A negatively curved universe could also be finite, folded through a pattern too complicated to visualize without mathematics. The word shape becomes inadequate. These are not objects with surfaces that could be photographed from outside. They are complete rules for how every location connects to every other. Two universes may share the same curvature and expansion history, while differing in how many paths join the same points, which directions eventually return, and whether a traveler comes back aligned with the orientation they had when they left. The topology would not be a feature inside the universe. It would be a property of what the universe is. One famous proposal involved a positively curved space whose fundamental region can be represented by a dodecahedron. Opposite faces are identified after a rotation. A beam of light leaving front face would return through another with its direction altered according to that rule. The model attracted attention because it appeared capable of reducing some of the unexpectedly weak, large-scale fluctuations in the microwave background. For a time, the fit seemed suggestive. Then the expected matching patterns failed to appear convincingly in improved data. Searches did not find the circle pairs that a sufficiently small version of the model should have produced. The idea was not eliminated in every possible form, but its most accessible versions lost much of their appeal. This is how topology research often moves. A model explains one feature. The same model predicts another. The second prediction is absent. The parameter space contracts. The topology retreats beyond the region where it would have been easiest to see. The process is scientifically healthy. It is also revealing. We are not choosing among a few visible shapes. We are attempting to infer the global structure of space from a narrow set of fossil signals, each damaged by noise, foreground emission, incomplete sky coverage, and the fact that we occupy only one location. The problem resembles trying to reconstruct the floor plan of an enormous building while confined to one room. Using echoes that have crossed corridors no one can enter. Some echoes return, most do not. Walls absorb part of the sound. Other noises interfere, and the building may still be expanding while the measurement is made. Even that comparison is generous. A room has boundaries that can be reached in principle. The cosmic horizon is not a wall. It is the limit of causal access. As expansion accelerates, some regions that are visible now will eventually become unreachable, and some are already beyond any possibility of receiving a signal sent today. The universe does not merely conceal its topology behind distance. It may be carrying the evidence away. This is why future surveys matter, even though none can remove the fundamental limit. More precise maps of microwave polarization could reveal correlations that temperature measurements alone cannot isolate. Large-scale surveys of galaxies and quasars can test whether spatial patterns repeat under unusual rotations or translations. Maps of neutral hydrogen may one day probe immense volumes of cosmic history, with more statistical samples than current galaxy catalogs provide. Gravitational waves could offer another route. Unlike electromagnetic radiation, primordial gravitational waves would carry information from earlier conditions and interact differently with matter along the way. If detected across the sky with sufficient precision, their background patterns might provide an independent test of global connectivity. A compact topology could restrict their allowed modes just as it restricts other fluctuations. But each new messenger remains inside the same universe. Every photon, gravitational wave, and particle reaches us only through paths permitted by the topology we are trying to discover. We cannot step outside the system to compare its map with the territory. We cannot place detectors beyond the horizon. We cannot repeat the universe under different initial conditions. Cosmology is forced to solve an inverse problem with one sample. This becomes especially dangerous when a candidate topology fits an anomaly. Given enough possible spaces, variations, sizes, and observer positions, some model may resemble an unusual feature by chance. A pattern discovered after examining many alternatives does not carry the same weight as a prediction made before the data were inspected. The universe can appear designed for a model simply because the model was shaped around the universe we happen to observe. Researchers therefore look for multiple linked signatures. A viable topology should not only suppress one set of microwave fluctuations. It should also generate the correct correlations elsewhere, remain consistent with polarization, avoid forbidden duplicate structures, fit the observed curvature, and survive increasingly precise surveys. The demand is severe because the claim is severe. To identify cosmic topology would be to discover that directions we treat as independent are physically connected. It would establish a total architecture for space, not merely a new object within it. And it would alter what we mean by the size of the cosmos. In an infinite universe, every increase in the observable horizon reveals new volume. In a compact universe, deeper observation may eventually stop adding new territory. It may begin adding new views of territory already seen. The distinction would remain hidden until the first unmistakable repetition. Before that moment, every new galaxy could be another place. After it, the sky would have to be reconsidered as a network of paths. Some distant structures would remain independent. Others might be the same matter observed at different ages. The apparent inventory of the universe would shrink. Distances would still be real, but they would no longer guarantee separation. Two objects on opposite sides of the sky might be closer through a route we do not normally use than through the path their light took to reach us. The cosmos would not become small in any ordinary sense. Even the most compact surviving models would exceed scales that human travel can approach. But infinity would no longer be available as a silent assumption. That may be why the question feels larger than geometry. An infinite universe permits endless elsewhere. No matter how much remains unexplored, more space always waits beyond it. A finite universe removes that escape. There may be no endless reservoir of unseen regions. No guarantee that reality continues with new stars, new galaxies, and new possibility without limit. The apparent abundance of the sky could be partly repetition, stretched across different directions and different eras. We have not found evidence that this is true. What we have found is that the universe can hide the answer almost perfectly, and the better our models become, the clearer the trap appears. Every observation is local. Every signal is delayed. Every survey ends at the same causal boundary. We are trying to determine whether space returns to itself while standing inside a region that may be too small for anything to complete the journey. A larger telescope does not solve every problem by seeing farther. For cosmic topology, distance is useful only while new light can still arrive. The observable universe grows because time passes and signals from more remote regions finally reach us. That sounds as though the horizon will eventually expose the whole structure. Given enough patience, perhaps a returning beam will complete its circuit. Perhaps duplicate galaxies will emerge. Perhaps the shape of space will become obvious. Accelerated expansion changes that expectation. Regions sufficiently far away are carried from us so rapidly that signals emitted there now will never arrive. The horizon is not a temporary inconvenience waiting for better engineering. It is built into the causal structure of an expanding universe. If the shortest route around space lies beyond that accessible region, time may never reveal it. This produces three different possibilities that can lead to nearly the same observations. Space may be infinite. Space may be finite but much larger than the observable universe. Or space may contain compact directions, whose signatures were weakened by inflation, hidden by our location, or pushed outside the range where light can complete a loop. The first possibility is usually treated as the default. It is mathematically simple and consistent with the data, but it is not an observation. No survey has measured an infinite distance. No instrument has counted an unlimited number of galaxies. Cosmology measures curvature, expansion, matter distribution, and radiation inside a finite horizon. Infinity enters when those measurements are extended beyond everything that they can be checked. That extrapolation may be correct. It may also be the largest assumption in the model. A civilization appearing billions of years from now could face an even narrower sky. Distant galaxies will have crossed beyond its observable reach. The cosmic microwave background will be stretched to wavelengths increasingly difficult to detect. That civilization might build accurate local physics while reconstructing an incomplete cosmic history because crucial evidence had already disappeared. We live in a more favorable era. We can still see billions of galaxies and the afterglow of recombination. Yet the topology may already belong to a category of facts that reality permits but does not guarantee any observer can recover. That means some global properties may be underdetermined by all possible evidence available from one causal region. If two models produce the same local physics and the same observable sky, choosing between them is not merely difficult. Within that region, there may be no experiment that can decide. One universe continues forever. The other closes just beyond the farthest path any signal can travel. The difference is enormous and locally silent. A finite cosmos would place a limit on spatial volume at any given cosmic time. There could still be more matter than we can see, perhaps vastly more, but not an endless amount. The number of galaxies would be finite. The number of causally separated regions would depend on topology and action, rather than extending without bound. This changes questions often asked, as though infinity were already established. Does every physically possible planet exist somewhere? Are there regions with histories almost identical to ours? Must rare events occur without limit, because there are infinitely many opportunities? Those conclusions require more than a large universe. They require assumptions about its total extent, statistical uniformity, and the range of possible physical states. A compact universe would remove the simplest route to inevitable repetition. Similar worlds could exist. Exact duplicates would not be guaranteed merely by endless volume, because the endless volume would be gone. At the same time, topological repetition would create a different kind of duplication. Multiple images would not represent separate copies of matter. They would be different records of the same matter. The sky could repeat without reality repeating. Apparent abundance could come from light, taking several routes through one limited domain. That distinction reverses the usual intuition. An infinite universe may contain places that resemble us because there is room for coincidence to recur. A compact universe may show us the same place repeatedly because there are several paths to it. One creates duplicates through quantity. The other creates them through connection. Without identifying the topology, the sky may not tell us which kind of repetition we are seeing. there is a deeper consequence. Cosmology often assumes that what we observe is a fair sample of a larger whole. The principle works because the universe looks homogeneous on sufficiently large scales. But if the observable region wraps across a fundamental domain, our sample may not contain as many independent regions as it appears to contain. Some directions could be statistically linked by the global architecture. The model might still fit many measurements. The error would lie in how much independent universe we believed those measurements represented. A confirmed topological signal would therefore force astronomers to rebuild catalogs around identity rather than direction. They would need to determine which structures were unique, which were repeated views, and how much cosmic history each path had added. The farthest object might not be the most remote place. It might be a familiar region reached by a longer route. No such identification has survived scrutiny. The sky continues to behave, within present limits, as though its distant regions are independent. Each failed search pushes the minimum scale outward and makes the simplest compact models less plausible. But it does not convert a lower bound into infinity. That conversion happens quietly, because language demands a noun where the evidence provides only an inequality. We say the size of the universe when the measurement gives the size of the observable universe. We say space is flat when observations show that curvature is close to zero within uncertainty. We say the universe may be infinite because no returning pattern has appeared within the distance available to test. Each statement is reasonable. Together, they can create more certainty than the data contains. The careful answer is less satisfying. The universe is at least as large as the region we can observe, and simple repetitions on smaller scales have not been found. Beyond that, the total extent of space remains unknown. Not poorly measured, unknown in a way that may survive every improvement in measurement. The evidence has narrowed the possibilities, but it has also exposed a harder question. What if the universe is large enough to hide its finiteness forever? Suppose the search succeeds, not with a suggestive alignment or a statistical oddity, but with a pattern too precise to dismiss. Two regions of the microwave sky match after the exact rotation predicted by a compact topology. Independent surveys find corresponding structures at different apparent ages. Polarization follows the same relationship. Competing explanations fail. The result would not reveal an edge. It would reveal that no edge was ever necessary. The first measurements would give us a scale and a connection rule. They might show that space repeats after a distance larger than the observable radius, or that one direction closes more quickly than the others. From that rule, cosmologists could reconstruct a fundamental domain, the smallest region containing every unique location in the universe. Everything beyond it on a mathematical map would be another representation of the same territory. For the first time, humanity could estimate not merely how far we can see, but how much space exists. The number might still be incomprehensibly large. A compact cosmos could contain more galaxies than any civilization could visit before stars disappear. Finite would not mean reachable. It would not make intergalactic distances less severe, or weaken the expansion carrying most of the universe away from us. But it would remove infinity from the physical description. That change would reach beyond cosmology. Infinity often enters scientific reasoning as an idealization. Equations describe infinite space because it is mathematically convenient and because no boundary is observed. Statistical arguments assume unlimited volume. Philosophical claims use endless space to make rare events inevitable. A measured topology would place those arguments under a new constraint. There would be only a finite amount of matter at a given time, only a finite number of galaxies, only a finite number of physical experiments being performed by nature in separate places. Events could remain extraordinarily numerous, because opportunities never end. The universe would no longer guarantee another chance somewhere else. That would not make Earth central. It would do almost the opposite. In a compact space, there may be no geometric center at all. Every location would occupy the same global structure. Our importance would not increase. Our assumptions would shrink. The night sky would also acquire a different meaning. Today, every direction appears to open toward new territory. A confirmed topology would turn some of those directions into routes. Looking outward would no longer mean looking away from home in the simplest sense. A telescope aimed across enough distance might be looking toward the region containing the Milky Way, reached by a path so long that it shows an era before the galaxy had its present form. The universe could contain a record of our surroundings scattered across the sky. Most of that record would be too old, faint, distorted, or obscured to recognize. But its existence would follow from the topology. Information leaving a region would not necessarily disappear into an endless exterior. Some of it could circulate, delayed by the full scale of space. Nothing about this permits escape from time. A returning image would not restore the past. It would only deliver old light. The event itself would remain finished. The civilizations in that image, if any existed, would not be waiting at the distance where we see them. They might have vanished before the signal began the final part of its route. Topology could return information. It could not return what the information describes. That may be the most severe version of a finite universe. Space could connect back to itself, while history continues in only one direction. The roads return. The moments do not. Even if the cosmos is compact, accelerated expansion may prevent light from completing future circuits. A topology that once allowed repeated images could become harder to detect as distances grow and wavelengths stretch. The universe would preserve its global connections in geometry while placing more of them beyond practical use. A finite cosmos could still become observationally fragmented. Distant regions would fade. The microwave background would cool and redshift. Future observers might inherit a sky containing fewer clues than ours, even though they occupy the same total space. The architecture would remain, but the evidence for it could disappear from view. We may therefore be living during a narrow interval, when the question can still be investigated. That does not mean it will be answered. The most likely outcome may be continued constraint. Better maps will rule out smaller domains. Larger surveys will eliminate more patterns. Polarization data will tighten the search. Each result may push the shortest possible loop farther beyond the horizon without ever detecting one. The universe will continue to look infinite, and that appearance may remain indistinguishable from a finite reality whose scale exceeds every available path of evidence. Science can tolerate that uncertainty. It often has to. A model is not weakened merely because some questions lie outside observation. The standard cosmological framework does not require us to know the global topology before it can describe expansion, structure formation, or the microwave background with remarkable precision. But precision inside the horizon should not be confused with possession of the whole. We know how the observable universe behaves. We know that simple small topologies have not announced themselves. We know space is close to flat on the scales we can test. We do not know whether those scales eventually repeat. That ignorance is not a temporary blank, waiting automatically to be filled. It may be imposed by the same physical laws that make observation possible. Light needs time to travel. The universe has a finite age. Expansion limits which paths can ever reach us. A global fact can remain real while producing no accessible local signature. The question at the beginning was whether some galaxies might be the same region, seen more than once. The deeper question is now harder. What if no repetition is visible because the universe is infinite? And what if no repetition is visible because the universe is only large enough to keep its boundaryless shape beyond every test we can perform? Those possibilities lead to different realities. One contains endless new space. The other contains a finite amount of space arranged so completely that no observer inside it can prove where it closes. From here, both can look identical. The universe may be larger than we can imagine, or it may be smaller than it looks, with every apparent direction, opening not into infinity, but into a structure that eventually returns to itself after the evidence has already run out.